Hello everyone, welcome back to this channel. Dear students, today's topic is pole zero plot for the two-port network. This is the topic related to subject electrical circuits for second year engineering students. I have already explained the basic concepts of two ports networks, that are Z parameters, Y parameters, ABCD parameters and H parameters. So next part is we have to plot the diagram of poles and zeros related to the two-port network. For this, we need to know some formulae of Laplace transform. You don't have to learn all the things related to Laplace transformation. These problems, we will be solving a few numericals on this part. These problems are pretty simple. Only these three equations you need to memorize, and which is again simple. R stands for resistor. If you are working with RLC in normal domain, that means in time domain, then how to transform the terms into Laplace? It is given by this formula. R remains as it is in Laplace. L is the inductance. If you transform L using Laplace transformation, its value becomes S into L. This term S is the notation used in Laplace transformation. Like we use notation T for time period in normal domain. Likewise, S is the notation in Laplace transformation. So value of L becomes S into L. Value of capacitance C is transformed as 1 by C into S, where C is the value of capacitance. We will solve few numericals, then these things will be more clear to you. Before solving this numerical, I would like to explain one term which is commonly used, that is known as transfer function. It is denoted by H of S, which is ratio of Laplace transform. This LT stands for Laplace transform of output to the Laplace transform of input. This is the basic definition of transfer function. When we solve numericals, then we might get the equation like this. K is some constant. In the numerator, I will be getting S minus Z1, then S minus Z2 and so on, divided by the denominator term is expressed as S minus P1, S minus P2 and so on. As I mentioned right now, we'll solve the numericals, then these concepts will be more clear to you. Presently, I am explaining the basic things. So, after getting the value of H of S, you will be having some numerator term, some denominator term, and multiplying factor will be K. This is immaterial as far as poles and zeros are concerned. The roots of numerator, that is Z1, Z2, Z3, etc., are known as zeros of a system. They are denoted by small circle. Then the roots of denominator term, keep in mind S is the notation used in Laplace transformation, whereas Z1, Z2, Z3, P1, P2 will be having some values. So roots of denominator, that is P1, P2, etc., are called as poles of a system, denoted by notation cross. Let us solve one numerical to get an idea how to make use of this pole zero diagram, or how to draw the pole zero diagram. I will draw one circuit. This is, suppose, the given circuit. Resistance is 4 ohm. Then inductor is having value 1 Henry. There is one more resistance in vertical branch, that is 1 ohm. And in parallel with this, we have a capacitance 1 farad. Suppose this is the given network. The question is like this: some network will be given and it will be asked obtain the driving point function and plot poles and zeros. What is the meaning of driving point function? This port is known as input port. If you calculate impedance from this port, it is known as driving point function, denoted by Z. Now, first step, all these numericals we need to solve making use of a Laplace transformation. I have written the formulae. So first step is convert the given diagram using Laplace transformation. As we discussed, resistance remains as it is. So this is the value of resistance, 4 ohm. Similarly, this 1 ohm is resistance. Both these values remains as it is. In place of inductor, What is the notation? What is the formula? L is transformed as S into L. L is the value of inductance. What's the value of inductance in the given diagram? It is 1 Henry. So I will write it like this. From this equation, I am making use of this equation. 1 Henry transformed to S into 1. As I mentioned, S is the notation in Laplace transformation. So we will keep S as it is. S into L, value of L is 1. So it is S into 1, that means only S. So I will replace this value by notation S. Resistance remains as it is. For capacitance, I have to make use of this formula. So capacitance is changed, converted into 1 by Cs. C is the value of capacitance. Value of capacitance is 1. So this transformed as 1 upon 1 into S. Simply it becomes 1 by S. So in place of 1 farad, I will be writing new value 1 by S. This is now the equation diagram which we have transformed into Laplace domain or Laplace transformation. Input impedance in this case, once you will draw the diagram using Laplace transformation, is denoted by Z of S. That means now the diagram which we are referring is in the Laplace domain. Now next part is I have to calculate equation of Z of S. What is asked in the question? Calculate driving point impedance. Impedance is Z. Since we have transformed equation into Laplace, it is Z of S. How to do the calculation? If you are looking from this terminal, start doing calculations from the opposite end. That means from this end. Simple logic. If I am doing calculations from this end, these are two different wires. Whenever two different wires are there, the values are in parallel, because two different wires are there, so current is different. So these two things are in parallel. So for these two, I will write the equation 1 parallel 1 by S. Very simple. These are two different wires, so I am considering these two things in a parallel. Now, if first combination, I have started calculation from this end. If first combination is in parallel, next combination will be in series. So I will write it like this. Plus, series means plus sign, plus these two are already in series, they are in same line. So I will write this as plus 4 plus S. And this equation will be equation of driving point function, that is Z of S. Only you need to identify the starting thing. Starting elements are in two different wires, so they are taken in parallel. It is 1 parallel 1 by S. Remember, these are already in series, which are shown in the diagram, given diagram. So it is 4 plus S. So I have written this formula. Let us simplify it. We know how to calculate the value of parallel combination. It is 1 into 1 by S. Multiplication of these two terms divided by addition of these two terms. 1 plus 1 by S plus 4 plus S remains as it is. Now I have to simplify this equation. I will write it like this. 1 into 1 by S is simply 1 by S upon. In the denominator, I will take LCM, so it becomes S plus 1 upon S plus 4 plus S. Now this term gets cancelled. So remaining equation I will write like this. 1 upon S plus 1 plus 4 plus S. Now let us take the LCM, that is multiply this 4 and S by this term. So next equation can be written as Z of S is equals to this 1 remains as it is, plus 4 into this term, plus 4 into S plus 1, plus S into this term, plus S into S plus 1 divided by S plus 1. Simply I have taken the LCM. Let us simplify it further. 1 plus, multiply this every term inside the bracket by 4. So it is 4S plus 4 plus, multiply S plus 1 by S. So it is S square plus S upon S plus 1. So it becomes 4 plus 1, 5 plus 4S plus S, 5S plus S square upon S plus 1. To make the thing simple, rearrange the equation like this. I will simply rearrange the equation. So the equation now can be written as Z of S is equals to S square plus 5S plus 5 write the values in the descending orders of power. So s square plus 5s plus 5 upon s plus 1. Now, this is the equation of transfer function. I will tell you the simplest trick. This is one part. I have to draw the pole zero diagram. What we learned, the roots of numerator are called as zeros, roots of denominator are called as poles. In the denominator, I have simple term s plus 1. So how to calculate root of this? Very simple logic. Equate this term, denominator term, s plus 1 is equals to 0. This will give me the value s is equals to minus 1. Roots of denominator term are called as poles. So this whatever value you are getting minus 1, it is represented by first pole. There is only one pole whose value is minus 1. Very simple trick. If there is only one term, there is not the term related to s square, s cube and so on, directly equate that term to 0, calculate value of s. Whatever you are getting, that is known as pole because it is related to denominator term. So pole is at minus 1. What about zeros? Zeros are roots of this numerator term. You need to do the calculations of roots of this term on the calculator. If you do this calculation, first root on the calculator, that is denoted by, these roots are denoted by zeros because these are the roots of numerator term. So first root will be minus 1.38. Second root, that is z2, is minus 3.62. These are the two roots which I got after doing the calculations on the calculator. Now next part is how to draw the diagrams of poles and zeros. To draw the diagram, the simple technique is draw x and y axis. On x axis write real part. RE stands for real part. On y axis mark imaginary part. IM stands for imaginary part. This is the origin. Look at the value of pole. Pole is at minus 1. This is the origin. Towards RHS I will be having positive values. Towards LHS I will be having negative values. So first pole, there is only one pole. First pole is at minus 1. Let us say minus 1 value is somewhere here. So I will write this as P1 is equals to minus 1. The poles are denoted by notation cross. Then 0 is at minus 1.38. So 0 will be somewhere here. Zeros are denoted by small circles. Say this is the value of Z1, which is equals to minus 1.38. One more 0 I have, that is minus 3.62. So let us say this 0 is somewhere here. Again I will denote it by small circle. This is Z2 whose value is minus 3.62. This particular diagram is known as the pole zero diagram. Now let us solve one different numerical which contains some imaginary terms. Suppose this is the given network. Question is similar to the previous one. Calculate input impedance or driving point impedance and draw pole zero diagram. First step, like the previous sum, but the calculations are altogether different compared to the previous sum. We need to transform the given circuit into the Laplace domain by using same formulae what we discussed in the last numerical. Resistance remains as it is. This is inductor of value 1/2 henries. For inductor we have the formula S into L. Value of L is 1/2. So this 1/2 henries gets transformed. I am using this formula S into 1/2, that is 0.5 S. Next, this 1 henries will get transformed as S into 1, that is simply S. About this capacitor, value of capacitor is 1/2 farad. So I will have to make use of this formula. So value is 1/2 farad. It gets transformed as 1/1/2 into S, which is 2/S. Now after converting these values into Laplace, you need to draw the new diagram. Presently I am writing the values of Laplace equivalent in the same diagram. So this inductor becomes 0.5 S. This inductor becomes only S. This capacitor becomes 2/S. So these are the values what we obtain after transforming the elements using Laplace transformation. Now this is the part from where you have to calculate the driving point impedance. So like the previous sum, you need to do the calculation from the remaining end, that is from this end. Now think like this. These two elements, they are in same wire, that means they are in series. As I mentioned earlier, you just have to identify whether first element is in series or parallel. If it is in series, next will be in parallel, third will be in series, and so on, because this type of networks, this type of circuits are called ladder circuits. So always there is a alternate changes. So these two elements are in same wire, that means they are in series. So for these two elements, I will write the equation as 2s plus s, because these are in series. I will mark a bracket for this series combination. Since I have taken this is in series and it is a ladder network, next combination is in parallel, so I will mark the sign like this, in parallel with 0.5s. I will write one more bracket for this term. Now I have taken this in parallel, so next will be in series, so it is plus 1. This entire thing is denoted by Z of S, which is driving point impedance. Now let us simplify this equation. I will take LCM for this part, so this square bracket remains as it is, so it is 2 plus s into s square upon s, in parallel with, this symbol stands for parallel, 0.5 into s plus 1 remains as it is. Let us solve this parallel combination. We know the rule. In parallel combination, I have to mark it like this, 2 plus s square upon s into 0.5s divided by 2 plus s square upon s plus 0.5s. Follow the rules of parallel combination. In the numerator take multiplication, in the denominator take addition, plus 1 remains as it is. Let us simplify it further. This 2 plus s square term is getting multiplied with 0.5s. So every term, I mean first I will take multiplication of these 2 and 0.5. So it becomes simply s plus, this becomes 0.5s cube. I have multiplied 2 plus s square by 0.5s. So it is 2 into 0.5, that is only s remains, s square into 0.5s, 0.5s cube upon s. This term I have kept as it is, divided by this numerator term 2 plus s square remains as it is. I am taking LCM, so multiply this value by s, so it becomes plus 0.5 s square divided by s plus 1. This last term I have kept it as it is. Now this s denominator of each term gets cancelled, so write down the remaining equation. Like I will write it like this, Z of s is equals to s plus 0.5 s cube upon this 2. Now s square plus 0.5 s becomes plus 1.5 s square. This is s square, 1 s square plus 0.5, so it is 1.5 s square. So I have simplified this term, plus 1. Now let us take LCM, so it becomes s plus 0.5 s cube plus this term. I will have to simplify it further, so it can be written as, I will multiply 1 by this entire term, plus 2 plus 1.5 s square upon 2 plus 1.5 s square. Now what I mentioned earlier, be habituate of writing the equations in terms of decreasing powers of s. So first I will write 0.5 s cube, then next will be plus 1.5 s square plus s plus 2 upon 1.5 s square plus 2. This is the answer of first step, where we calculated the value of driving point impedance. Now we have to plot pole zero diagram. Before that, I will mention one more thing. What could be the possible variation in such numericals? We have calculated driving point admittance. It can be asked, calculate driving point admittance. We have calculated impedance. It can be asked, calculate driving point admittance. follow the same steps, you will get equation of Z of S. If admittance is asked, only simple formula you need to apply. Admittance is Y of S 1 upon Z by S. That means take the reciprocal of this equation, you will get the equation of admittance and follow the procedure. The remaining procedure is same. Alright. So in the present numerical, it is asked to calculate driving point impedance that we did, and we have to plot the pole zero diagram. How to draw the pole zero diagram? For drawing the pole zero diagram, we need to calculate roots of numerator and roots of denominator. Strictly do the calculations on the calculator. So roots of numerator term are known as zeros. So I will do the calculation on the calculator. Directly I will write the values. These zeros, roots of numerator, are denoted by Z1, that is first zero is minus 2.79, second value of Z2 minus 0.5 plus J 1.19. In Calci I gets displayed. One very important thing, if you have older version of Calci, while calculating Z2, only minus 0.1 is displayed. Directly this value will not be displayed, but on the top right corner of Calci you will see this notation REC. Whenever you are calculating roots and this notation is displayed, it means that first this part, real part, that is minus 0.1 is displayed. You need to press equal to sign, then this value will be displayed. In new versions, directly this value will be displayed on the calculator. Alright, so this is second root. Third root, that is third zero, is minus 0.1 minus J 1.19. These are the three roots of the numerator term which are called as zeros. Now poles. Poles are roots of denominator term. Again, do the calculations on the calculator. So poles will be J 1.154 and second pole minus J 1.154. These are the values which you will get after doing the calculations on the calculator. Now this is different numerical. Values are imaginary. How to draw the diagram for such parts? Like the previous case, x-axis is real axis, y-axis is imaginary axis. This is the origin. Before starting, I will mark few values. Look at the values. One is minus 0.1, this is real part, and J, imaginary part, is plus 1.19 and minus 1.19. To make the thing simple, first I will mark some points. See, this is the origin, this is imaginary axis. So somewhere here, I will get plus J 1.19 and another value of J is 1.154. So let us say this value is 1.154 and another value is J 1.19. Similarly, on the lower side, I will get minus J 1.154 minus J 1.19. Now, how to mark the poles and zeros? First zero is at minus 2.79. For this, there is no imaginary term. It is real term only. It is on the real axis and it is minus, so it is at the negative side. So somewhere here, let us say I will get this value Z1, whose value is minus 2.79. What I taught you, zeros are denoted by small circles. So this is first value of Z1 which we completed. Z2 is minus 0.1 plus J 1.19. How to do it? It is minus 0.1. So let us say minus 0.1 is somewhere here, minus 0.1, and value of J is plus 1.19. So this is plus 1.19. Take the intersection of these 2 points. There is minus 0.1 and J 1.19. Whatever point you are getting, that is second zero, that is Z2. It is intersection of minus 0.1, this value, and plus J 1.19. Third zero, minus 0.1, same value, minus J 0.19. That means this part, again take intersection of these 2 points. Whatever point of intersection is there, it is the third zero, Z3, whose value is minus 0.1 minus J 1.19. Now, about the poles. First pole is at J 1.154. Poles are denoted by notation cross. So, the first pole is like this. This is first pole P1. Second pole is minus J 1.154. So second pole is here, that is P2. So this is the diagram which shows the plot of poles and zeros. So dear students, I have covered the different types of variations which can be asked about the pole zero diagram. That's it for today's session. If you like this video, don't forget to smash the like button. Thank you very much.